Good morning, everyone, and welcome to lecture number 32. So, so far we have looked at two paradigms for algorithm design, and we also looked at data structures, which play a crucial role in implementation of algorithms. Okay, so far we have looked at the first paradigm was divide and conquer. And the second one was greedy. And then we looked at data structures. So divide and conquer is kind of, I mean, see, both divide and conquer and what we are going to see, dynamic programming, all of them have similar features. I mean, in the sense that you uh, obtain sub-instances. Okay, so here what you have is, so divide the problem into sub-instances. And somehow join them into a global solution. Solve and then join. So greedy has a slightly different feature. Okay, so this is characterized by greedy choice and optimal substructures. Okay. So, however, the limitation of both of these problems are so divide and conquer is kind of applicable in many cases. So there are many algorithms, whereas greedy happens to be, so problems that have greedy solution happen to be very structured. Okay, so we saw that so the underlying structure is matroids. Okay, so they're closely related to matroids. So probably that is the reason not many natural problems admit greedy algorithms. Okay, as you would have seen in the quiz questions itself. Yeah, we'll discuss it later. So some of you would have got about clique or independent set and so on. So all of them, they don't admit greedy algorithms. So pick any random problem, it's very likely that it won't admit greedy algorithm. Okay? So that's a limitation of greedy algorithm. But however, this is perhaps the simplest strategy. Okay, so that's the reason why even if it does not give optimal or best solution, in the real world, people end up using greedy algorithm for their simplicity. Okay, and many a times on random instances, they on an average they also perform good. Okay, so today we are going to see what is known as dynamic programming. So this programming is actually a weird term. Okay, uh, which is again, which also has this optimal substructure property, which also requires optimal substructure property, but it's more versatile. Okay, what I mean is it's applicable to almost all of the problems. So dynamic programming can be used for almost all of the problems. Okay, so yeah, so so this was a dynamic programming idea existed for centuries, but there was no formalization. The formalization happened only in the 1950s. This is due to, I think, Bellman. Okay, so who worked for US military, and he coined this term to avoid scrutiny from military. Okay, so military officers didn't really like mathematical terms, so he just uh, so used the idea and called it as dynamic programming, which even till date the same terminology is being used, just to avoid scrutiny from military officers who didn't like mathematics. Okay, so I'll start with a very simple example to demonstrate the idea of dynamic programming. And today's lecture, we'll be seeing a couple of more examples that demonstrates dynamic programming. So all of us would have seen Fibonacci numbers. These are also known as Virahanka numbers. Okay. So, so they are recursively defined in the following way. I mean, there probably are first examples in solving recurrences in discrete maths course. Okay. So f of n is f of n minus 1 plus f of n minus 2 with the initial conditions as f of 0 is 0, f of 1 is 1. Okay. Suppose we want to compute fn when n is given as input. Okay. So we want to compute as fast as possible. One naive implementation would be just write this as a recursive program. Okay. That's it. Okay. So let's call this as fib. So fib n, if n is 0 or 1, you return the corresponding values. Else you call fib n minus 1 plus fib n minus 2. Okay. So there are two recursive calls. So the time complexity, you can see that, so you can just, so recursively, so if you write this time complexity, so t of n will be less than or equal to t of n minus 1 plus t of n minus 2. Okay. It so happens that the time is also bounded by the value of the function computed. Okay. Because you are making a call with n minus 1, making a call with n minus 2. So that is why. So plus, you might require order of 1. Okay. So plus order of 1. Because you'll have to do these tests. Okay. So you can see that using the Fibonacci recurrence, you can see that this is exponential. Okay. So this is something like, so this is roughly bounded by, in fact, this is more precisely 1 plus root 5 by 2 at the end. Okay. Roughly. Up to a constant multiple. Okay. So that way this procedure is not really useful. We are given n as an input. So we expect running time to be something small in terms of n. Okay. So one way is to use our famous closed form expression for Fibonacci sequence. I hope this is right. Okay. Using golden ratio. Okay. So this gives you explicit formula. All you have to do is powering. So you have to multiply this n times, multiply this n times, and divide by root 5. But only thing is, the problem is this is not even a rational number, square root of 5. Okay. So managing it is difficult because the end value is going to be integer. Okay. And we'll have to use approximations of this. Okay. So square root 5 is not a rational number. So you cannot have a finite representation. Okay. So only thing is you can approximate. Then, yeah, you may not even get an integer here if you approximate. Okay. So that is a limitation of this closed formula, though it's handy. I mean, it's a nice formula, non-recursive formula. So one simple way, in fact, this has been done for centuries. I mean, people had figured it out a long time ago. So you can actually convert this recursive algorithm into what we call as dynamic programming, okay, or an iterative procedure. So this is called memoization. Okay. So one observation is the following. Okay. So the crucial observation, this is typical of all problems where dynamic programming comes into rescue or gives efficient algorithms. Okay. So if you look at this, so see, this running time is exponential, fine. But how many different calls are there? So if you look at it, so the calls are basically fib n, fib n minus 1, etc., etc., fib 2, fib 1, and fib 0. Okay. So there are only n plus 1 distinct calls which are going to be used. So they are used in an exponential fashion. I mean, the combination is exponential, but there are only these many values. Okay. So one attempt is you reuse them, you don't recompute. See, what would happen is if you draw the recursion tree for this, there will be lots of reuses. Okay, so fn by 2 or fib n by 2 will be called multiple times, which is kind of unnecessary. Okay, so what you can do is you can store these values. So you can store fib 0, fib 1, then use it to compute fib 2, and so on. Okay, that's a very natural iterative algorithm. So here it is. So the iterative version is you initialize the initial element of the array. So f is an array, f0 is 0, f1 is 1. Okay, so you start with the index I equal to 2, while I is less than or equal to n. You set fi to be f of I minus 1 plus f of I minus 2. I haven't put the increment here, I mean, because this is not a full program as such. So what you do is you compute it iteratively. So you know f0, you know f1. Now f2 is basically this plus this 1. Okay, so f3, this plus this is 2. f4, this plus this, which is 3, and so on. Okay, so what is the complexity of this procedure? So you need to run the loop from I equal to 2 to n. So number of iterations is n minus 2, and you are doing one arithmetic operation, addition. Okay, so time is order of n arithmetic operations. Okay, if you are looking at bit complexity, each arithmetic operation, so how long these numbers be? So the number could be as big as 1 plus square root 5 to the n. So this can be log n bit. Okay, so addition of two log n bit numbers would require log n bit. So if you take bit complexity, this is going to be order of n log n bit complexity. Okay, so yeah, just to check, so I hope I am audible. Okay, so order of n, good. Okay, so I somehow don't get any alert for when you type a message. Okay, so this is one classical example of dynamic programming. Okay, so this is called dynamic programming. What you do is you kind of use solutions for sub instances to obtain solution for the given instance. Okay, so you combine it in a nice way. So here there was no optimality. Okay, you just wanted the value. Okay, so there is no maximization and so on. So in typical applications, there will be either minimization or maximization. Okay, so that is what we are going to see next. We are going to see two examples, both of which are maximization problems. And in the next lecture onwards, we are going to use kind of dynamic programming. So for example, to compute shortest paths. Okay. Yeah.
Hello.
Yes. Yeah.
Sir, so every recursive algorithm can be written in an iterative fashion.
Yeah.
So one thing is that we still use recursion even though we know that we can do in iterative way. Is there any like mm, uh, perk of using a recursive algorithm over a iterative algorithm?
So see, usually recursive algorithms are simple. Okay. So simple to write, simple to code. Okay, computationally there is a lot of overhead there because when you execute the recursive algorithm, it's likely to be slower than the iterative version. Okay, but people still do use it, particularly for its ease. Okay, so I mean, It just usually recursive algorithms are shorter, right, compared to iterative.
Yes.
Yeah. So if efficiency is not an issue for you, then you would use recursive algorithms.
Apart from like it being intuitively easy for us, there is no other perk.
There is, I mean, it depends on the problem instance, but like I said, I mean, yeah, for recursive algorithm, there is no other perk as such.
Okay, sir. Thank you.
Yeah.
Sir,
Yes.
could you explain how bit complexity is n log n?
Yes, that's because these numbers, right? They can be n bit long, right? Oh, they can be n bit long. Okay, so not log n then. Okay, I'm sorry. They're not log n bit long. They can be n bit long, right? So it could be order of n square. Yeah, thank you. Because it can be as big as 1 plus square root 5 to the n, so n bit long. Yeah. So this could get, numbers can be n bit long. Okay, so one more thing, I mean, before we go to the next problem. See, even this is not efficient, okay? We cannot consider this as efficient because this is kind of not polynomial in the size of the input. Okay, so even the arithmetic see, you cannot really avoid this addition of n bit numbers and so on. So if you are interested in only the arithmetic operations, you can even do slightly better. Okay, you can do much better, in fact. See, the problem here is n is log n bit number, right? If you represent n in binary. Okay, so if you have polynomial in n, that will be exponential in the actual input length. Okay, so yeah, so there are algorithms which actually do it in so there are algos that use order log n operations. But however, you cannot overcome this n factor there because it, again, even that solution will involve addition and multiplication of numbers which are n bit. Okay, so that could be costly. So you'll require at least order of n time for addition of n bit numbers. Sometimes, I mean, there are some algorithms which also use multiplication. In that case, it will be slightly bigger. Okay, so that way this is not really efficient. This is just a demonstration where you can get rid of exponential in n. Okay, this is not exponential in the input length. That is something you might have seen in the case of primality testing, if you have seen it. Given n, check if n is prime or not. So there the catch is you can always do it in root n time, square root n time, but the catch is n is given in binary. Okay, so that's the reason why that algorithm is not efficient. Okay, so let's come to our first problem for today. Okay, so this is about computing subsequence, which is common to given two strings. Okay, so let's just to be define what is a subsequence. Okay, so consider a string. Say the characters are x1 to xn in the string. Now, any substring is you just pick a subset of letters and write it in that order. Okay, so for example, if you take, say, x is a b c d x a m, some arbitrary. So a subsequence is you just pick some of them. So I pick this, I pick this, 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 this. This is a subsequence. That is a b d a m. Only thing is you have to preserve the order. Okay, it's not a subset. So now the problem is the following. We are given two strings x and y, could be of different lengths. So let's say this is of length m and length n. Okay. So the output is length of a longest common subsequence between x and y. So you consider set of all subsequences of x and look at set of all subsequences of y. Okay. And look at their intersection and pick the longest one. Length of that is our output. Okay. Maybe in some cases you might also want to output the actual subsequence. Okay. So this kind of problems are very common in, for example, I think biocomputing, okay, or bioinformatics, where these strings will be representing DNA sequences. So when you compare two DNA sequences, right, you might want to look at subsequences which match. Okay, so that is how you compare DNAs. I mean, that's one of the subroutines for comparing DNAs. Okay, so it's a very naturally occurring problem. So I'll just demonstrate with an example. Okay, so let's say x is the string ACAMBDA. So x is ACAMBDA and y is BADAMBDDA. Okay. So then the longest length of longest common sub. So I wrote LCA. It should be LCS. Okay. Subsequence is 6, which is you take this sequence AAMBDA. So you can have AAMBDA. Okay. So our algorithm should output 6. We'll also see how to output the actual subsequence as such. Okay. Is the problem definition clear? Okay. So yeah, so let's just try to get a kind of recursive algorithm, and well, it is easily an iterative algorithm too. So for that, let's just try to see. I mean, so what we do is, so we'll have this value LCS ij is the length of a common subsequence between prefixes of x and y. Okay, so that is, you consider a prefix of x starting from character 1 to character I, and prefix of y starting from character 1 to j. Okay, so that is, so if I consider LCS, say 2 3 is basically, you consider first 2 letters here and first 3 letters here. Now what is LCS between? So this value should represent the length of longest common subsequence between these prefixes. Okay. So now we have the following observations. Okay. So what we do is, so to compute LCS ij, so what is it we want really? So we want LCS mn, right? We are assuming that length of x is m, length of y is n. Okay. So we want LCS mn, where length of x is m and length of y is n. Okay, this is what we want to compute. So a natural way is, you look at the last character in both the strings. Okay, so we look at the last character, either they are equal or not equal. Okay, so accordingly we split into two cases. So the first case is the last characters are equal. So let's look at this. So the last characters happen to be equal. If I take I as 1, 2, 3, 4, 5, 6, 7, I as 7, and this has how many? 3, 3, 6, 3, 9, 7 and 9. Okay, I as 7 and J as 9. So these are the last characters. Now, if they match, so how do we compute, or how do we can we reduce computation of LCS ij to smaller instances? Okay, so when I say smaller instances, you should have a number less than I or a number less than j. Okay, so let's just make the following observation. So I claim that we can always have a longest common subsequence of these strings, which are prefixes of the original string, that is x1 to I and y1 to j, that will match these two last letters. That is, xi and xj will always be matched. So let's see why is that so. So I'll just use the same example here. So the claim is there is always a longest subsequence which matches these two. Do you see why? So you consider two subsequences, let's say x prime and y prime, okay, such that they are equal. Now, so if I claim either the last letter of x or the last letter of y must be matched in this, be a longest common subsequence, then x prime and y prime must match the last letters, match either last letter of x or y. Why is that? So either the last letter of x has to be matched by some position in y, or the last letter of y must be matched by some position in x. What happens if not? If not, I can extend that sequence, right? I can extend by matching these two. I know that these two are equal, so otherwise I can extend this into a longer sequence. So I know that this is the longest subsequence. So hence either A is matched with something or this A is matched with something here. Okay. But in that case, I can match as well the last letter here, right? So if this letter is being matched somewhere, say here, okay, I can match it as well here without violating anything. Because that is also a subsequence, right? So let's say, yeah, so here this example, it's not very easy to demonstrate that. So what I'm saying is, suppose A is matched elsewhere, say A is matched here. So A is somehow matched somewhere here, okay? So this was an A, let's suppose. Now I can consider y prime by dropping this A, but considering this A. It's the same y prime. Y prime does not change. So what I would have done is I would have matched this A with the last A here. Okay. So that way I can, without loss of generality, assume that there is always an LCS of these strings x and y, which are basically prefixes of the original x and y, that would match xij with y, xi with yj. Sorry, this should be y. Okay. Yeah. So I mean, the argument is just what I said here. Is mentioned here. So suppose there is an LCCS that matches xi with some yj prime, j prime less than j, then we can match it with yj as well, because we can just consider the same sequence. If I remove yj prime and add yj, it's the same sequence. Nothing changes. Okay. So the recursion for this part is the following. So LCS ij in this case is 1 plus, so 1 for matching the last. We'll be removing the last characters from each of the strings. Okay, so that is LCS I minus 1 comma j minus 1. Okay, so this is the recursive formulation for the case 1. The case 2 is the last letters don't match. That means for sure one of them has to be ignored, right? So accordingly we have the recurrence. So LCS ij is max of, you remove the last letter from x, that is LCS I minus 1 comma j, and the second recursive call is remove the last letter from j. You take the max of the two. That's going to be your value. Is the formulation clear?
Sir,
Yeah.
in some example, in some contrived example, both of these can be ignored, right? The last letters, if they are different, can they?
They can be, but we don't know, right?
No, since we are explicitly considering this case where we're ignoring only one of them,
Yeah.
so
No,
I'm just
see, it could be that in this recursion, right, you are also ignoring. So you'll go further j minus 1. Okay. See,
okay, okay,
that condition is not lost, right? So ignoring both is not lost. So both of them have that as sub instance, right?
yes, sir, yes, sir.
Yeah. Okay. So yeah, so this is also a natural recursive solution. Okay, so the recursive solution is this. So LCS Sn, so S is the first string. This is X and Y. Okay, so I just copied the algorithm from the notes. So the notation is from the notes. Okay, so first string is S and the second string is Y, T, and length is kind of flipped here. Okay, so it's basically, so if the last letters match, so last letters match, then the corresponding recursion is this. Last letters do not match, the corresponding recursions are these. You take the maximum, you return the maximum of the two values. Okay. So exercises. So prove that the above algorithm requires 2 to the min of m comma n time. Okay. In the worst case. You can just write down the recursive tree or write down the recursive function. Yeah, in fact, it will be slightly bigger than this. It will be 2 to the min of mn into something. Okay. Nevertheless, so this procedure is running in exponential time. So it's really not desirable as such. Okay. If there is a better solution, that is what we would like. So here is a simple iterative algorithm, iterative version of it. So the observation is again the same. Okay. So how many recursive calls are possible here? If you stare at this recursion, I mean, this is a straightforward implementation of this case analysis, right? Nothing else. You just write this as a recursive function. So you just check if xi is equal to xj, then you make this call. So LCS I minus 1 j minus 1, and then add 1 and return this value. And if they don't match, then you make these two calls and return the maximum of. Okay. So the first observation is, so how many distinct calls are possible? So if we ignore this string as a parameter, right? I mean, because once I know these values, say this is my I and this is my j. Once I know these values, it's all about these values here, right? So the recursive calls possible are LCS 0, 0, LCS 0, 1, LCS 1, 0, etc., 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 LCS MN. This is what we want, or NM. Okay. So total number of different calls is bounded by order of Mn. In fact, m plus 1 into n plus 1. Right? It's just like similar to Fibonacci. Okay. So the number of distinct calls or values that you want are basically n plus 1, f0 to fn. Okay. So similarly, number of distinct possible values are only this. Okay. So we can look for a natural iterative procedure, right? You know what is LCS 00, you know what is LCS 01, you know what is LCS 10. All of them are zeros. Okay. So you can start with the computing LCS 11, then LCS 12, LCS 21, and so on, in an iterative fashion. So by this formula, so LCS ij is defined either, so using these three values, LCS I minus 1 comma j minus 1, LCS I minus 1 comma j, LCS I comma j minus 1. So these are the three values that you require. Okay. I minus 1 j minus 1, I minus 1 j, I j minus 1. So you can just imagine you are having these values are stored in a table. Okay, so I'll just demonstrate using the example given in Bloom's notes. So I'll just follow that example. Okay, so you can build this table. Okay, so on the row you just write the string. So we have written here the second string y here. Okay, and we have written x here. Okay, so now, so this is LCS 11, this is LCS 12, this is LCS 13, this is LCS 14, and so on. This is LCS 21, 22, 23, 24, etc., etc. So this will be LCS 33. This will be LCS 35. Okay, and so on. So now what you do is you fill the table. So you start with, so this is trivial to do, right? LCS 11. So this is LCS 11. This is LCS 12. This is LCS 21, and so on. Okay. So to compute ijth entry, so what you need is, so you just look upwards. Okay. So the entries that you need to compute to are basically, so this can be computed from this, from this, from this. You look at these three values and compute. So how do you go? So you go diagonally up if the two characters are equal, or you go vertically up and horizontally left and see these two values, take the max of. Okay, so for example here, so you either, so yeah, so this is D and A, so you cannot take the diagonal value and add it. Okay, so you look here and look here, take the max, so 3. Okay, so for example 2 here. Okay, so B and B match, so you have to go diagonally up. Okay, so you have to go one value back and add, so you get 2. So you look at, so that's a possible, that's the only possibility, right? So you get this as 2. So this table can be computed in a very natural bottom-up fashion. You start with this value, and then how will you go? You go right once, down once, and then go diagonally down. Then right once. You can also compute this, compute this, compute this, then diagonally down, and so on. Okay. So this way you can naturally compute all these values. In fact, I think you can even compute all these at one shot. You can go, yeah, you can go like this. Okay, so that is also fine. So you can view this LCS values as a table, and you can fill. Now you can write a for loop. I mean, write two for loops, right? So one, you just go. So yeah, so the top row you can immediately compute, right? You can compute the top row and then come the next row, and so on. So at any point of time, the values required to compute the current I mean LCS ij are already computed. So with this, because one is to the left, up, or diagonally up, to the left. Sorry. Okay. So I'm leaving it as an exercise to write a nice iterative procedure. So write an iterative procedure that, given x and y, fills the above table or fills the matrix above, and outputs LCS length of x, length of y. Okay. Yeah, can somebody tell me quickly the time required for doing this?
Order of MN.
Yeah, so it's basically for each entry, right? How much time that you require? You'll have to compare the corresponding characters and decide whether to take this or this. So in either case, you will be doing one arithmetic operation and one comparison. So order of one operations. Okay. So arithmetic operation we can kind of ignore. I mean, you can just assume it as order one. This is because the numbers are going to be log n bit, right? So log mn, log of m plus or log of max of mn. Okay, bits are required. In fact, min. Okay, so common subsequence cannot be longer than the smaller string or shorter string. So the number of operations is going to be m into n. Okay, so the time complexity of this procedure is going to be m into n. So is the procedure clear to everybody? I don't want to describe the procedure, but if there is any doubt, I can clarify now. Ooh, 8:45. Okay, so we'll spend a couple of more minutes on the same problem. Just that's again one more. See, this is one way of non-recursivizing, iterativizing a recursive procedure. But so this is called dynamic programming. Okay, so what we do is we actually solve sub problems. So these are all sub problems. Okay, so this is our problem. So this value is what we want. Okay, so all these are sub problems. So there are lots of sub problems. So we considered all possible sub problems in this case. Okay, so we are lucky that the number of sub problems were not too much. Okay, so even if you go through all possible sub problems, and that's what we had to do to compute this table. Okay, it's only order of mn. Okay, it's quadratic in the input length. So let's say m is equal to n, then it's going to be order of n square. Okay, it's at most quadratic in the input length, not more than that. So it can be that in some problems where the sub problems could be exponential, that is when dynamic programming gets tricky. So we will be seeing this later. Okay, so for now what I'm going to do is I'm going to relook at this recursive procedure. Okay, and we'll see how to convert this procedure itself, recursive procedure itself, into polynomial time. Okay. So let the recursive procedure stay, but you can convert this into polynomial time. The trick is again using memoization. Okay, so memoization is basically you're remembering values, previously computed values. Okay. This is not memorization, this is called memoization. Okay. Yeah, I don't know why it is called memoization though. So what you do is, see, like I said before, there are only these many distinct calls, right? So in this recursion, when you write down the recursion, so LCCS say ij might be called many times because it runs for exponential time. It might be called exponential many times. But what we want is once it called for the first time, the value is stored so that you reuse it every time it is called next. So a simple way to do this is you have an array, two-dimensional array, which stores values when as and when they are available. Okay. So once I get result as LCCS whatever n minus 1 comma n minus 1 plus 1. Okay. So now I'll store LCCS nm. So next time in future, if I want LCCS nm, I can use that. Okay. So here is the implementation of it. So we use array nm. So we initialize these as unknowns initially. Okay. So some flag you can use, say -1, because once you have, I mean, you cannot have negative values for common subsequence. So you can use, set it as -1. Now what you do is you just put this check. If the value is not unknown, that means it has been computed previously. So initially everything is unknown, so nothing is computed. You return that value. Else you apply this procedure. Okay. So you compute using recursion. So once you compute using recursion, store that value result in the corresponding array. So now this becomes known. This is not no more unknown. Okay. So as soon as LCCS ij is computed, array ij will have that value. Okay. Yeah. So this takes some time to sink in. Okay. So I just want you all of you to think about it offline. Okay. So run this algorithm on some instances. So this is one simple trick. Okay. So this is, in many cases it just works, particularly when the sub instances are polynomial many, not many. So what you can do is, but your recursive algorithm runs for exponential time. So what you can do is you can have a matrix, two-dimensional or three-dimensional, depends on the parameters, or single dimension array, which stores the values. Once available, it stores the value. Okay. So this ensures that, so if any subsequence, say I'm looking at ij, okay. So once I have entered array ij as result, any other recursive call making call to LCCS ij will use array ij. It will never make another recursive call. Okay, so that is this check. So this part is check the values available. Check if values available. If so, use it. Okay. So this is a simple trick for memoization, and this comes. I mean, this is very common in dynamic program. We'll see another example. I will not really go into the details of this. Yeah, I can take a quick question.
Sir, how is this like better than the iterative approach?
See, no, I didn't claim that this is better.
No,
This
I'm
is
just
another
asking,
way
is
of
it
doing it.
better?
I would say iterative is still better because it never makes any recursive calls. Okay.
Okay.
Yeah. So see, the moment you make recursive calls, right? I believe you have done operating systems, right?
Yes.
and the programming languages, so how they are implemented. So there is a context, right? So there is a context which, I mean, okay, so at least operating system won't come into the picture, but in any programming language implementation, so you will have to store the context of this process, right? Which, I mean, procedure which makes a call. So all these values will have to be stored. So there is a natural overhead. So for any recursive procedure, there is a natural overhead there. So that way, efficiency wise, recursive procedures are never good. Okay, no matter what, because there is always huge overhead. So whatever the context of this program, you will have to store all of them. Okay, so it's called heap. Okay, so the heap will contain all the variables. In this case, not many variables, but still these parameters, right? They will be stored. So that way, it's not good. This is just a demonstration of another method of reducing the complexity of a dynamic programming solution. Okay.
This is a blend of both top down and bottom up.
Yes,
Because of this
kind of.
recursion.
Yeah, yeah.
The iterative one was cleanly bottom up approach.
Yeah, iterative was, yeah, that's a good point. Iterative one is clearly bottom up. Yeah.
Okay, sir. Thank you.
So, sir, both iterative and recursion, or the iterative version and this version, they both are an example of dynamic program because they both use memoization.
Yeah, yeah. So they're both dynamic program. Yes.
Okay.
Yeah. So typically in most of the dynamic programming algorithms, you don't really have recursion at all. Okay. So you come up with a recursive formulation, then make it iterative. Okay. So that's exactly what has happened here. So this is just an example where you can also have the same recursive procedure. See, sometimes recursive procedure might be easy to understand or whatever, right? Easy to read and so on. By making a minor modification, you can also have a procedure which runs efficiently. That's all. Okay, when I say efficiently, I mean with polynomial time, whatever.
Hello?
Yeah.
Sir, so whenever we do both recursion as well as storing the previous values, is it called memoization? Like, it is called memoization.
So memoization in both cases. See, memoization, at least what I understand from the definition, is basically like you store the previously computed values and use them. That is called memoization. Okay. There need not be recursion. There can be just iteration. That's also acceptable.
This is just another way of doing
Yeah, so here
memoization.
I put memoization, making memoization for the recursion. Okay, so memoization for recursion. Sorry, this won't come. Yeah, memoization for recursion. Okay. So memoization is a general term where so this is also memoization. So filling this table matrix, right, bottom up, or the way it is written, it's top down, but it's actually earlier entries are done first, or smaller instances done first. That is also memoization.
Okay, sir. Thank you.
Okay, Srinivasa, can you stop the recording?
Yes, sir. I do, sir.
Yeah, thank you.